Hello, everyone. I'm Hao Jiang from the University of Chicago. Today, I'll introduce our work of CodecDB, a columnar database that uses a data-driven approach to select encoding for data columns and uses the encoding knowledge to improve query efficiency. We are interested in columnar databases because in this big data era, we have a huge amount of data to fit into OLAP systems for processing. To process data at this large scale efficiently, most OLAP systems are backed by columnar databases for their extraordinary query performance. Columnar storage formats and columnar databases dominate the research fields and commercial market. Please see these familiar names, and I can easily list more. Improvement in columnar database efficiency thus makes a big impact on both research and real-world applications. It is clear why we need compression in databases. Many organizations keep all their data on cloud these days. The large scale of data makes saving especially important. Compression makes data size smaller, which saves money in storage and data transfer. However, there are two reasons that compression is often overlooked in row-wise databases. First, row-wise database blends data of all types together, and we often have to rely on general-purpose compression methods such as gzip and snappy to compress it. Many encoding algorithms designed for only one data type cannot be used. This brings another problem. gzip-like algorithms are block-based compressions, which means to access one row, entire data block need to be decompressed. In addition, they are computationally intensive and makes query slower. Lack of alternative methods and impact to performance make compression in row-wise databases less attractive to both researchers and the industry. So how are things different in a columnar database? First, columnar databases store data from the same column together. This allows different compression algorithms to be applied individually to each column. Many encoding algorithms designed only for one data type can also be used. This greatly expands the space of available algorithms. Second, unlike gzip and snappy, which encode data in blocks, many encoding algorithms encode data in records. The bits in the output corresponding to each record in the input can be accessed independently. If we want to fetch a record at a specific offset, we can skip directly to that position and only process the target. These changes brings a challenge to the study of compression in columnar databases. For a given data column, there can be many available encodings. How do we choose an encoding that compresses the data column most efficiently? Most encodings preserve records boundaries when compressing data. This brings new opportunities to improve the query efficiency of columnar database queries on encoded data. Here we show some examples. Bit-packed encoding removes excessive zeros from integer and tightly stores the bits. To execute a filter, we can directly compare the bits without decoding the data into integer. Using our SIMD library, we can also compare multiple entries in parallel, still without decoding the entries. The smaller the entries are, the more entries we can fit in a SIMD register, and the faster we can compare them. When we materialize the column with a filter result, we can use data skipping to skip the entries not needed. and only decode the target entries. CodecDB addresses the challenges and takes opportunities. CodecDB provides a data-driven encoding selection approach. It chooses encoding algorithms based on the data column characteristics and achieve efficient compression. To do this, we collect a large set of data columns from real-world data sources and train a neural network to make the selection. CodecDB builds an encoding-aware query engine. Most previous query engines decompress data before making queries and do not care what encoding the column uses. CodecDB maintains the encoding each column is using, allows the query engine to directly read encoded data, and provides operators optimized for each encoding algorithm. These operators integrate the encoding knowledge and the latest research effort to perform faster queries and materializations on encoded data. CodecDB also provides an extensive evaluation of query execution performance on various benchmarks. Our data-driven encoding selection contains two phases, training and inference. In the training phase, we collect a set of data columns, extract features and ground truths from each column, then uses the feature to train a classification model. In the inference phase, we obtain a data column to be encoded, sampling from it, extract features from the samples, and uses the model to perform inference to choose the encoding to be used on that column. We collect a large dataset consisting of 20,000 data columns from various real-world data sources. These sources cover most application scenarios and make sure our model is general enough. We choose features that are relative to the effectiveness of encoding algorithms. For example, cardinality is related to dictionary encoding, record length is for bit-packed encoding, and shortness is crucial to run-length encoding. We experiment with multiple machine learning algorithms with the features and choose the neural network, which gives the highest accuracy. Popular query engines, such as Presto, execute queries on encoded data columns in an encoding-oblivious way. The encoded data is first decoded into memory and accessed by the query engine. Query engine does not know and does not care what encoding the column is using. CodecDB employs an encoding-aware query engine, which knows what encoding each column is using and optimizes access to it. Here are some examples. On a bit-packed column, CodecDB can use XBoost, which is a SIMD library we developed to direct filter the encoded data without decoding it, generating a bitmap as filter result. When accessing other columns, it can use a bitmap to skip encoded entries not in range, also avoid decoding them. On a dictionary encoded column, we can consult the dictionary to know how many distinct entries it contains and use an array when performing aggregation, which is much faster than hash aggregations. We can also rewrite predicates using the dictionary and convert all the predicates to predicates on integers, which runs comparisons much faster. CodecDB provides a set of database operators for each encoding type that allows efficient query executions. It chooses appropriate operators based on the encoding type of the target data columns. This optimization utilizes knowledge of columnar encoding and try to save execution time and memory footprint when processing them. CodecDB implements the storage engine in Java and Scala. It trains the neural network model using TensorFlow. The data tables of CodecDB are stored on disk in Apache Parquet format. Parquet is an open source columnar storage format supported by many query engines, such as Spark and Presto. This also allows us to easily do apple-to-apple performance comparison against other query engines. For performance concern, we implement the query engine in C++. We evaluate CodecDB's performance from both encoding selection efficiency and query speed improvement. For the former, we compare against 3 approaches: Abadi's decision tree, Parquet's encoding selection, and exhaustive encoding selection. For the latter, we run TPC-H benchmarks on CodecDB against 2 popular query engines, Presto and the commercial solution DBMS-X, and also run SSB benchmark against these 2, as well as a research project, MorphStore. We test the data-driven encoding selection approach on a large corpus of real-world dataset. We separate the data columns of string and integer type and test them separately. The reason we choose these 2 types is twofold. First, string and integers are 2 of the most popular types, comprising most of the dataset. Second, although double is also a popular data type, for double data, we don't have enough encodings to use, making the encoding selection trivial on it. We compare against Abadi, a decision tree-based encoding selection algorithm, and Parquet's built-in algorithm, a rule-based encoding selection. Result shows our approach delivers higher accuracy than competitor methods and compresses data close to the exhaustive approach, which always achieve optimal compression. To evaluate the query performance, we run TPC-H benchmarks on CodecDB and compare with 2 competitors, Presto and DBMS-X. Presto is a popular distributed query framework supporting Apache Parquet file format. CodecDB executes benchmarks 10 to 25 times faster than Presto. DBMS-X is a commercial columnar database solution. DBMS-X does not have a good support to Parquet format, so we use its proprietary data format, which has a larger size than CodecDB. Nonetheless, CodecDB is still 2 to 10x faster than DBMS-X. These results strongly suggest advantage of optimizing query based on columnar encodings. We also compare CodecDB against a recent research project, MorphStore, on star schema benchmark. MorphStore compresses the intermediate results to reduce memory footprint and improve query efficiency. CodecDB is faster than competitors by 2 to 5x when comparing to MorphStore and DBMS-X. It also consumes less memory on intermediate results. Takeaways for CodecDB. CodecDB uses a data-driven encoding selection to choose the best encoding for each data column. CodecDB designs a query-aware encoding-aware query engine for better query efficiency on encoded column. CodecDB provides an extensive evaluation results comparing to competitors in various scenarios. Thank you.